Okay, students. So in the last portion, we derived the solution of least squares for skinny pole rank matrices. What I'm going to do now is I'm going to actually slightly go through the derivation in detail, right? So even though we said fundamentally the idea is to draw up a perpendicular, right? So but that's mainly geometric, right? That's not algebraic. So let's say somebody asks you from first principle, how do you get the same thing, right? So you can derive it also. You can also get that same intuition algebraically. Okay, so suppose x star is such that A transpose B minus AX star equal to 0. Okay, that means the error is orthogonal to data. Okay, error is orthogonal to data. Then x star minimizes AX minus B to norm square. Okay, so this is what I am claiming, right? And my claim is mainly coming from geometric intuition, but you can also, I am saying, you can also do it algebraically, right? This is how you do it, and this is how you see in most textbooks, even in your textbook on Boyd. This is how you'll see it, right? So you'll start with the norm of AX minus B, right? What you want to show is, ideally, you want to show that this value is the smallest when x is x star, right? In other words, for any x, right, the value of the least squares is at least as much as the value of the least squares when you pick this x star. That's what you want to show, correct? Fine. So to do this, and what you do is you start from the left hand side and you try to introduce x star somehow here, right? So you do ax minus b, right? So what you do is you write it as I'll add ax star and I'll subtract ax star, okay, on the left side. This is just so that we introduce x star into the expression here. Okay. So now here, what I'm going to do is I'm going to write it as a times x minus x star plus ax star minus b. Okay. Also, this is how I'm going to write it, right? So here I'm going to apply your standard, norm expansion. So I'm going to take the transpose of this and multiply it with this, and if you do that, you'll actually get something like this, right? You'll get a times x minus x star whole square, right, plus a times x star minus b whole square, okay, plus there will be like a 2ab term, right? What will be that 2ab term? Will be 2 times the transpose of x minus x star multiplied with ax star minus b. Okay, that's what you will get, correct? So here all I did is I take this norm square and I write for any vector, the square of the norm is equal to the transpose of the vector times the vector. That's all I'm using here, and when you write, that's what you will get, right? Let's delve into this term a bit deeper. So here this is just going to be x minus x star transpose a transpose times ax star minus b. Okay, now by the orthogonality principle you already forced this to be 0, this term to be 0, right? This here is this is the error and this is the data. Okay, so this term is already 0, so I can simply ignore this whole thing, right? Simply ignore this whole thing. Then what I'm left with is just 2 terms, this term here and this term here. Okay, and as you see, both of them are square terms, so you can immediately conclude that this is always going to be greater than or equal to ax star minus b whole square. Okay, that's clear? It's always going to be greater than or equal to ax star minus b whole square, right? Because this term here is always non-negative, right? This term is something non-negative greater than or equal to 0, and you're adding it to this, so always increase the value. Okay. Furthermore, you can actually say more. Furthermore, you can say that when do you have equality? When are this and this equal? Right? They are equal when this term is 0, right? And when is this term 0? This term is 0 when a times x minus x star is 0, right? That only happens when x equal to x star, right? Because the columns of A are linearly independent, correct? This is essentially some linear combination of columns of A that is 0, right? That's only possible when the coefficients themselves are all 0. So x must be equal to x star. Okay, so this actually establishes algebraically and more rigorously that x star is the unique minimizer, or rather the unique solution to least squares. Okay, x star is the unique solution to least squares. Okay, fine. Okay, so suppose we actually pick this x star, then what is the minimum value, right? Let's actually just compute what is the minimum value, right? The minimum value is ax star minus b norm whole square, correct? And you can write it as a times x star is a transpose a inverse a transpose b, right? Minus b whole square. Okay, so this is just going to be something like I minus a. So this is just one way of writing it. A transpose inverse A transpose B. Okay, you can see that is actually going to be the minimum value of the least squares problem. Okay, and it's achieved for that particular x star. Okay, so this is the key here. This expression can't be written enough number of times. A transpose A inverse A transpose B. That's the main idea. Okay, a couple of comments. One thing that you will notice here is that this expression is linear in B. I'll explain what that means. Linear in B. Okay, meaning that suppose if I are trying to force a vector B to be equal to Ax, right? Let's say some vector b1 to be ax and b2 to be ax, right? Then if you look at b1 plus b2, right, and you solve the least squares problem corresponding to b1 plus b2, meaning you try to minimize this. Okay, then the x star that you will get will actually be the sum of the x stars for the individual problems. Okay, because this is linear in B, right? So ultimately all this is some matrix times B. Some matrix times B, and that matrix is, has this formula, but it's just some matrix times B ultimately, correct? So it's a linear expression in B. Okay, so we'll look at some ramifications of that in a later lecture as well. Okay, also this ax star is actually the point on. So it's the second comment, I am of A, that is closest to B, right? So expanding Ax star, you'll actually get A transpose A inverse A transpose B. Okay, so in some sense, if I given a vector B, if I want to find a vector in the image space of A that is closest to B, then this will be the expression. Okay, that means I'll multiply it with this matrix over here. Okay, so this matrix is called sometimes the projection matrix on IME, meaning that if you take an arbitrary vector like B here and you multiply it with this projection matrix, what you will get is a point on the image space of A that is closest to the starting vector B. Okay, well, we discussed a little bit of these things earlier also. Okay, now let us look at what if A is not full rank? Okay. What if A is not full rank? Okay, so if A is not full rank, it turns out that you can still find the minimum value of this. Okay, you can still find the minimum value of this. It's just that the minimizer will not be unique. Okay, why will the minimizer not be unique? Well, basically, the columns of A are linearly dependent, right? So if I construct one particular linear combination, right, I could maybe do a different linear combination that still gives in the same product Ax eventually, right? So I could change this vector x around and still get the same Ax, right? So that's what primarily leads to the non-uniqueness in the solution, right? So solution will be non-unique. In that case also, see, A transpose A will not even be invertible, so I can't use this formula basically. I can't use this formula, right? A transpose A will be non-invertible. Right? In that case, still you can find one of the minimizers to be something called the pseudo inverse of A multiplied with B. Okay, the pseudo inverse of A multiplied with B. Okay, so what is the pseudo inverse, right? So I'll describe what the pseudo inverse is. Okay, but the main idea is that if I want a solution to Ax equal to B, I'll simply multiply B with the pseudo inverse of A. Okay, so what is the pseudo inverse? There are many ways of defining the pseudo inverse. We'll look at some definitions later on, But for now, we'll just use the SVD to define the pseudo inverse, right? So suppose if you have A equal to U sigma V transpose, right? And let this be the thin SVD. Okay, so thin SVD meaning U here is an n cross, so A here is an m cross n matrix, U is an m cross r matrix. Okay, sigma is an r cross r matrix, and V is an n cross r matrix. Okay, so R here is the rank of A. Okay, so basically the idea behind a thin SVD is you have your SVD, you remove all the zero singular values, that's it. Okay, if A is rank R, you know that it has R non-zero singular values, so keep only those R non-zero singular values here. Okay, so this becomes a square matrix and these two become rectangular matrices, right? The other variant is full SVD where U and V are both square matrices, but the sigma matrix is a rectangular matrix, right? So there are different variants of the SVD. So here, using the thin SVD, you can define the pseudo inverse to be equal to V times sigma plus U transpose. Okay, and what is sigma plus? Sigma plus is obtained by inverting. So remember, sigma is R cross R diagonal matrix, correct? Inverting non-zero diagonal entries. Inverting the non-zero diagonal entries and keeping the zero diagonal entries as they are. Okay, keeping zero diagonal entries intact. So for example, if your singular value matrix is something like 5 0 0 0, right, then sigma plus would be 1 by 5, okay, 0 0 0, something like this. Okay, however, in this context, because I have taken the thin SVD, right, because I have already removed all the zero singular values, this is going to be diagonal and all the diagonal entries are going to be non-zero. This scenario will not arise, okay, because in the thin SVD I have actually gotten rid of the 0, right? So you'll actually get something like you can simply have 5 and 1, and maybe 5 and 1 here. Then you simply take the inverse of all the diagonal entries, right? 5 and 1. Okay, so I can simply write sigma inverse here, right? I don't have to write sigma plus. Okay, in general, if you take the full SVD, the pseudo inverse is defined as A plus equal to U sigma plus V transpose, where sigma plus is defined like this. Okay, but if you take the thin SVD, you can just write sigma inverse V transpose. Okay. So this is what the pseudo inverse of a matrix is defined as. We can just take this as a definition of pseudo inverse, right? So some pseudo inverse can be defined for any matrix. It doesn't have to be square, fat, thin, as long as you can write SVD. And for every matrix, you can have SVD, right? So as long as you have an SVD, you can write the pseudo inverse, right? One interesting property of the SVD of the pseudo inverse is unique. Okay, every matrix has a unique pseudo inverse. I'm not going to prove this, right? Has a unique pseudo inverse. Okay. It's a bit counterintuitive because SVD itself is not unique, right? A matrix has many possible singular value decompositions. For example, you can think of the identity matrix. Identity matrix is like, you can write many SVDs for the identity matrix, right? So SVD is not unique, but pseudo inverse is unique, right? Okay, so that is the interesting point. So why pseudo inverse? So pseudo inverse actually solves the least squares problem irrespective of whether A is full rank or not. Okay, irrespective of whether A is full rank or not, right? So so X star equal to A pseudo inverse B is a minimizer. Okay, it may not be unique to AX minus B plus square for any A. Okay, for any A. Okay, so I'll expand on this in a minute. In particular, when A is not full rank, this is how you will find the solution to least squares. Okay. Now let us actually try to see if it syncs with we already know. Right? For example, we already know that if A is skinny full rank, then the minimizer has to be given by that formula A transpose A inverse A transpose B. Right? Let's see if it actually gels with that. Right? So let's try to compute the this quantity A transpose A inverse A transpose, and see that it actually computes to pseudo inverse when A is skinny full rank, right? So let's plug in the SVD here. So A transpose is going to be V sigma U transpose, right? So you can write V sigma U transpose times A is U sigma V whole inverse. A transpose is again V sigma U transpose. Okay, so I just written the thin SVD here, right? So let's recall that U here was like, you know, an N cross R matrix. This is going to be an R cross N matrix, U transpose, and U transpose U is going to be identity, right? Because U is like a tall matrix like this, okay, in which all the columns are orthogonal to each other. When you multiply it with transpose, essentially you're going to get a identity, R cross R identity matrix, right? Okay, so what you get here is so let me check. I think there is a missing transpose here. Okay, fine. So here what you get here is simply V times sigma square V transpose inverse V sigma U transpose. Okay, so let's if you work this out, right, if you take the inverse of this matrix, right, you will actually once again get V sigma power minus 2 V transpose, right? Remember that V transpose is the same as V inverse. Just do the math here and you'll get this sigma U transpose, right? And then by computing this and correcting for the algebra, you actually get V sigma U transpose, which is precisely the pseudo inverse. Okay, so you can see that the dreaded expression that we have here for the X star, what we have done here is actually written the pseudo inverse. Okay. Right. Similarly, you can also check that if A is square invertible, then the pseudo inverse is actually your usual inverse. Okay, fine. So essentially what is happening here is that the pseudo inverse is basically going to solve the system of equations. So it's going to solve the least squares problem no matter what A is. Okay. So in the next portion, we'll discuss the least norm